So one question you probably have is, if we already have a surface, how might we find a parameterization for it? We're definitely going to be needing to know how to do this for all the sections that that are going to come after this, the last three sections of our course. And the answer to this is going to depend greatly on what surface we're given. There are definitely various ways of finding parameterizations for various surfaces. Now, the simplest way is if we have let's say our surface is actually given as just a function of two variables, z equals f of x, y. This could be just as simple as picking x equals a u, y equal to v, and then in that case, z, if we replace x and y with u and v, is just f of uv. That is a simple default parameterization to fall back on, as long as we actually do have a function of two variables to work with. But there are some cases where, even if it is given this way, there are better ways of doing the parameterization. So we could say this is kind of our default parameterization. So maybe if we're dealing with a plane, so if we have a plane that we can actually fall back on some of the techniques from chapter 12, let's look at a particular problem. So here we're told to find the parametric equations, or find some parametric equations for a plane that passes through a particular point and contains two particular vectors. That's a pretty common situation, especially since that came up in our tangent planes already. Now here we could go ahead and just find an equation for it. We could go ahead and take the cross product of these two vectors. That's going to be a normal vector to our plane, and then we could find an equation from it that way. And that'd be perfectly fine, at least as long as you could solve for z. If the z component of our normal vector turned out to be 0, you definitely couldn't have a z equals something. But there would even be ways around it then. But that's actually a lot more work than we really have to do. If we actually go ahead and plot these points, so we're going to have the point, we'll call it A. It'll be the point 0, negative 1, 5. So we have this point sitting here in three-dimensional space. We take the vectors, starting at A, and they're modified by 2, 1, 4 is one of them, and the other one is negative 3, 2, 5. So we have these two vectors coming off of A. We want the plane that goes through those two vectors, or that goes to that point and follows those two vectors. Any other point in the plane determined by these, we can actually start at A and add multiples of, I guess they call them u and v, in order to actually get that other point. In other words, we can get any other point that we want, so something like x, y, z in the plane is going to be the point 0, negative 1, 5, plus, we'll go ahead and use u and v here, some multiple u of 2, 1, 4, and some multiple of negative 3, 2, 5. Or in other words here, x is equal to, 0 plus 2u minus 3v. Y is equal to, negative 1. We have a u and a 2v. We'll go ahead and write we'll write it as u plus 2v minus 1. And finally, z is equal to, we have a 5, we have a 4u, and a 5v. So 4u plus 5v plus 5. And if we use those as actual equations for a parameterized surface, again, we don't really have limits for u and v right now. Technically, u and v can actually go off to to negative infinity and infinity in either direction, um, because this plane doesn't really stop. So just GeoGebra does want me to pick some values, so I'm just going to pick values that are far enough that we don't really have to worry about it. They'll go off the screen, and we get our particular plane. Let's actually move this down so we can see a little bit better. But we can see that plane definitely goes through that point. It follows our two vectors like we want it to. And we also got the advantage of the point A here is actually represented by the parameters of 0, 0. This is where u equals 0 and v equals 0. And our vectors are following the grid curves. In fact, all the grid curves are going to be following those vectors for any point on this plane. Which, if those are particular vectors that are very important to a particular problem that we're dealing with, we might want our parameterization to have something to do with it, rather than getting some equation and having the parameterization have nothing to do with the original vectors that we started with, other than the fact that obviously they came from there originally. Another possibility might be something like a sphere. If we want to say parameterize a sphere of radius 4, which has the equation x squared plus y squared plus z squared equals 16, what we probably don't want to do is solve for z. If we had to solve for z, we get something like plus or minus the square root of 16 minus x squared minus y squared. We actually end up with two different surfaces here, technically. We have a top surface where we have the plus sign. We have a bottom surface where we have the minus sign. That means our top and bottom hemispheres have to be separate parameterized surfaces if we were to try our default parameterization. But we can actually do the entire sphere using one parameterization. Another problem with this parameterization would be that the actual base, the region that the x's and y's can vary over, is a disk rather than a rectangle. This would just be the circle of radius 4 in the xy plane. That's going to make anything that involves integrals a little bit more difficult, because we are going to do integration with these parameterizations eventually. Another thing is that around the boundary where x squared plus y squared is close to 16, or actually is equal to 16 if we actually have the boundary, then the derivatives actually can get rather big. If we were actually graphing this thing, so actually let's get rid of this. And we want to graph the equation z equals the square root of 16 minus x squared minus y squared. Because it doesn't like me typing in z equals that first. If I do that, it tries to make it into an implicit curve. So just type in the square root of 16 minus x squared minus y squared. It gives our hemisphere, our top hemisphere, because we only get part of the sphere when we actually solve for z. So you can, along the edges here, of course, the actual tangent planes are going to be very vertical. In fact, they are technically vertical along the actual boundary. And that's going to make anything involving derivatives there actually kind of an issue. Not something that we couldn't deal with, but using a different parameterization might make that a little bit easier to work with. Another thing you might have noticed when I was moving it around a little bit, along that edge, there's a little bit of tearing. That's because the function is actually changing quite a bit in that section. That's kind of involved with the whole derivatives being really big, and the fact that our boundary here is a circle rather than actual rectangle. So all those problems actually can be an issue in some applications, including computer graphics. This is maybe not the best way of doing a sphere in computers. So what we're going to do is actually take inspiration from spherical coordinates. Remember, in spherical coordinates, the equation of this particular sphere is simply rho equals 4. This is the sphere of radius 4, which is the radius equals 4. So if we take our two coordinates theta and phi as our parameters, that will actually give us a parameterized surface. So remember our equations: x is equal to rho sine phi cosine theta. If rho equals 4, then this is just 4 sine phi cosine theta. Y is equal to rho sine phi sine theta. And again, rho is just 4. And then finally, z is equal to rho cosine phi, which again is just 4 cosine phi. These are actual equations in terms of two parameters, phi and theta. And we can plot this as a parameterized curve, or parameterized surface, I should say. So if we plot this, we have the surface. We have 4 sine. I'm just going to use u and v here instead of phi and theta, just because, I need to type these in. And single letters are a little easier. So we have 4 sine u cosine v. We have 4 sine u sine v. And finally 4 cosine u. The u here is my phi. Remember, phi goes from 0 to pi. There we go. V is my theta. Theta can go all the way around from 0 to 2 pi. If I plot that, now I have the entire sphere. Or, I guess not the entire sphere, because part of it got cut off at the bottom. There we go. We have our entire sphere. And there's absolutely no issue. If I move this around, it actually, there's not going to be any tearing. It's actually fairly well behaved. And if you actually look at the grid curves, we can identify those as the lines of latitude and longitude. If you want to think about this in terms of the globe, the circles going around, those are where u equals constant. Those are, I say u because we have u here, but technically that's where those are the values for phi. So if phi is equal to pi over 2, we had the equator. If u is equal to maybe this one is pi over 4 or something like that. Probably not. I don't know exactly which ones they've chosen here. But for different values of phi, we have different latitude lines. For different values of theta, we have these other ones that are longitude lines. They're technically also circles, but they're actually great circles. They go around the entire sphere. So working with spherical coordinates as kind of a way of getting good parameterization of spheres are actually pretty useful. So a lot of times when you want to be working with some various surfaces that look like they should actually belong to either cylindrical coordinates or spherical coordinates, you might want to take inspiration from those particular coordinate systems. One last way of getting a parameterization for a surface that we're going to talk about here is a surface of revolution. Essentially here we take some curve y equals f of x. So we have some curve in here, and we rotate it around the x-axis. And that essentially turns into a surface revolution, and that's not very well drawn, but hopefully you got an idea of what we're doing. We're taking this curve and we're rotating around the x-axis, and we get a surface. Maybe for an example here, let's look at y equals. Let's go ahead and plot this instead. So we have y equals sine of x. That is a curve in the xy plane. I want to take that curve and I want to rotate it around the x-axis. I want to have some sort of surface along the x-axis. Now, what does that actually mean? Well, if I take a particular point on my curve, let's take the point pi over 4, comma, of course, the value at pi over 4 is square root of 2 over 2. That is a point on my curve, and that point, if I'm taking this curve around the x-axis, it's going to turn into a circle. We're going to have a circle centered on the x-axis, in fact, with a radius of pi over 4. Or not, sorry, the position on the x-axis that it's centered around is at pi over 4. The radius is going to be square root 2 over 2. In fact, I can go ahead and tell it I want the circle centered at the point pi over 4, comma 0, 0, because it doesn't have a y or z direction. It's on the x-axis with a radius of square root 2 over 2. Unfortunately, it gets a little bit complicated to just put in a circle because it doesn't tell it which orientation in three-dimensional space. If we were just looking down on the plane, we would try to graph it like that. But we actually want we can actually finish this up by giving it a normal direction to the plane that the circle's in, and that normal direction is just going to be along the x-axis. So I'm going to take a vector. Basically, I'm going to take the vector I, and that'll give me a circle centered on the x-axis, parallel to the yz plane through that point. And that circle is supposed to be on my surface. In fact, if I were to move that point along this, I should have a multitude of circles with different radii moving along the x-axis. Now, how do we actually turn that into a parameterization? Well, how do we parameterize a circle? We use trigonometry. If we were to look at a circle of radius square root of 2 over 2, centered at the origin, we'd have something like x equals square root 2 over 2 cosine theta, and y equals square root 2 over 2 sine theta. If we want to do that to actually get an equation for this particular circle here, well, we'd have to use y and z instead of x and y, and we'd have a fixed x value of pi over 4. So actually, if I were to take this particular circle out of there and graph the curve where x is equal to pi over 4, y is equal to square root 2 over 2 times cosine of, I'm going to put t in here instead of theta, and then z is square root 2 over 2 times sine of t, where t is just going to go from 0 to 2 pi. It gives me exactly the circle that I had before. That's exactly what I wanted. So we're going to go from this parameterization of a circle, of a general circle of radius square root 2, to instead x equals pi over 4, y equals square root 2 over 2 cosine of theta. So I'm basically making y play the role of x, and I'm making z play the role of the y. Now, can we do this in more generality? Can we do this without having a particular function already in mind? Well, where did this x come from? This x was just the x coordinate we plugged into the function. So actually, we're not even changing that x. We might say that x equals x, or we could give it a different letter if we want to. We could say that x equals u. Y and z, well, where do we get the square root 2 over 2? Well, that's what we got by plugging pi over 4 into the function. So we're getting the radius here out in front by just plugging in u into f. And then we could either keep using theta, or if we want to use u and v, we could change that to a v. This is a parameterization for a surface of revolution. And it's actually a pretty robust one. It works very, very nicely. If we go ahead and plot that in here, if we go ahead and make the surface where we put u, comma, so f in this case was sine of x, so we're putting sine of u times cosine of v. Then we have sine of u, again this is just f of u again, this time times sine of v. The u value, because this is our x value, technically we can have any x value along the x-axis. I'm just going to give it a big range of -10 to 10. But the v is actually is the one going around these circles. So we only need to go from 0 to 2 pi this time. And we get our surface of revolution, at least out to x equals 10. So we've taken our sine, our y equals sine of x curve, and we've rotated around the x-axis, and we get this kind of interesting looking, I don't know, beads on a rope kind of thing. But the point here is that even though you might actually even say that this is kind of an issue, that it kind of intersects itself, there's actually not an issue when it comes to doing the surfaces as a parameterized surface. But being able to work with surface of revolution this way is very, very, very useful. You could do things with this, like we could actually look at spheres if we wanted to. Technically, the sphere is the surface revolution of a circle. You could say look at cylinders as surface revolutions of lines. So are cones. This time, the line just isn't parallel to the x-axis. Any of those could actually be viewed as a surface revolution and could be parameterized in this kind of fashion. In fact, let's look at a surface that maybe you might not even thought about before. Let's think of a circle in the xy plane. I'm going to take this circle, let's center it at, let's say 1, 0, 0. Actually, let's move out to 2. I want it to be further away from the origin. We're going to have it have a radius of 1. And just because I want it to be in the xy plane, I'm going to pass it the vector 0, 0, 0, 1. That means that a normal vector to the plane that's in is just k. So that will force it to be in the xy plane. So we have a circle here. Actually, that's not exactly what I want. Let's move it to center on the y-axis. That'll be better. If I were to take this particular circle and then rotate it around the x-axis, what would it look like? Well, you might even be able to picture what that would be. It's going to be a very donut-shaped curve. Technically, we call it a torus. And we can use the parameterization that we found right here to actually find a parameterization for it. Now, technically here, we've actually written this in terms of, well, we actually haven't, I guess we haven't written down an equation for it. Technically, if we wanted to write an equation for it, we could say it's x squared plus y minus 2 squared equals 1 because it has center of 0, 2, and then it has a radius of 1. This is not actually the easiest way to deal with it. What we could do instead is parameterize this particular curve. We can use trigonometry for that. So we could do something like x equals cosine of t. Or let's even go ahead and give it a u. We don't want to set y equal to sine of u. Instead, we want y minus 2 to equal sine of u. Or in other words, we want y to equal sine of u plus 2. And these are cosine and sine without anything in front of them because the radius is equal to 1. If we go ahead and plot that particular curve, we should get the exact same circle. Of course, the u here is going to go from 0 to 2 pi because we're going all the way around a circle. And it didn't really seem to show up because it's just overlapping what we already had. It's the same circle. And now how are we going to parameterize it from here? We can't just immediately use the form that we have here because, well, here we're not letting x just be itself. Here we already have the x as some function of u, and we're going to need to modify that. Well, keep in mind what we're actually working with here. The f that we're putting here is the radius that we have at any given point. And it's always basically given by whatever the y value is. So essentially, we want the y value, or at least the y value that we have here, regardless of whether or not it's in terms of x or in terms of the u that we already have it in, to be our radius. And we're using that radius in order to make our circles. We didn't have to already know that pi over 4 and square root 2 over 2 were the center on the x-axis and the actual radius of the circle coming from the function at that point. All we needed to know that it was just the radius. So in essence, what we're going to be doing here is we're going to keep x the way it is. X isn't going to change. But we're going to let y and z be this radius of sine u plus 2 and sine u plus 2. But we're going to multiply them by a cosine of v and a sine of v. That basically says that for a given value of u, whatever x value on the x-axis that we're centered around is given by cosine of u, regardless of what that u is. That gives us our particular x value for our center. But then the radius, the sine of u plus 2, is then taken along a circle around the x-axis. So if we go ahead and plot that, of course here the u is still going to go from 0 to 2 pi. This v is also going to go from 0 to 2 pi. So let's take a moment to type in. So we had cosine of u. We had, make sure the sine of u plus 2 is in parentheses. That's being multiplied to cosine of v. And then we have the sine of u plus 2 multiplied by sine of v this time. U going from 0 to 2 pi. V going from 0 to 2 pi. And we get a torus. We get a donut. Technically, the donut would be the solid. We're actually include everything inside. Technically, this is just the surface on the outside. Same as what a sphere technically is. It's the outside of it. But the point here is that this way of parameterizing anything that is a revolution around a particular axis works even if it's not just taking a curve y equals f of x. If we have some curve of the form x equals some function of u and y equals some function of g, or some function g of u, we can always go ahead and turn this into a parameterization of taking this particular curve, or you can even say this is a vector valued function r of u equals f of u I plus g of u j. If we rotate this around the x-axis, the x doesn't change, and then the y value, the g, actually turns into just the radius times the cosine and sine of v. Or if we wanted to go around the y-axis, then instead of having y paired with the z, you'd actually use the x and the z. So you'd have f of u cosine v. You'd leave the y as just the g of u, and z would now be f of u sine of v. So various ways that we can actually rotate around an axis, any particular curve that we want to. So even in more generality than the book went into, I guess. But the point here is that there's multiple ways of tackling parameterizing surfaces. Sometimes you just have to play around with it, or recognize that it's a particular kind of surface, and so we can actually tackle it in whatever particular way we want to do so. All right, so I'm going to go ahead and leave this video here. I guess this video gave us a few techniques for tackling parameterizing surfaces. It wasn't maybe as structured as the last one or the one to come, but hopefully it's been kind of helpful. But what we're going to do in our third video is we're going to look at surface area of these surfaces. So if we're given a particular parameterized surface, can we find the area of that surface? So meet me there, and we'll get into that.